In this lesson, we are going to discuss force on a dielectric slab at constant charge. So this capacitor is charged and the power supply is now disconnected. Once the power supply is disconnected, charge is trapped. So Q will remain constant. Now here is a dielectric slab whose dimensions are same as the space between the capacitor plates. This dielectric slab is partially inserted into the capacitor. So X length of the dielectric is inside the capacitor now. Opposite charges will get induced on the dielectric, minus Qi here and plus Qi here. So these charges will experience a force in these directions and the net force will be inwards. We want to calculate that net force. Now since charge is remaining constant, we'll write the formula for potential energy in terms of Q. So potential energy stored in the capacitor will be given by Q square by 2C. Q is a constant, C is the thing that is varying as this dielectric enters, capacitance will change. So let's write this as Q square by 2 C to the power minus 1. So as this dielectric enters, capacitance will change. So the change in potential energy will be Q square by 2. If we differentiate this, the old power comes to the front. The power decreases by 1. We get C to the power minus 2 and we get dC. So therefore, this du becomes minus Q square by 2C square into dC. Since du is negative, potential energy is decreasing. So loss in potential energy, this loss will be used to do work to move the slab because no one else is there to do work, battery is not there anymore. So loss in potential energy is work done to move slab. So the loss in potential energy we have found out. That will be Q square by 2C square dC. Minus sign is only showing that potential energy is decreasing. So loss in potential energy is Q square by 2C square dC. And this will be equal to F dx, force into displacement. Force may depend on x, but since it's a very small displacement dx, okay, we can assume F to be constant and write F dx for that small displacement. So now we know the formula for C. Okay, we've got two capacitors in parallel, one filled with air and one filled with dielectric, and that capacitance we found out in the previous lesson. So this becomes Q square divided by 2C square. So C is epsilon naught B by D multiplied by L plus K minus 1 into X. And this C is getting squared. B is the breadth of the capacitor plates. L is the length of the capacitor plates, that is the same as the length of the dielectric. K is the dielectric constant. D is the distance between the plates. And X is the length of the dielectric inside the capacitor at this point of time. dC is differentiation of this. So this will become epsilon naught B by D, that is a constant, multiplied by differentiation of this. So here if you differentiate L, will get 0 because that is a constant, and we get K minus 1 into dx, and that is f dx. So dx will get killed, and that is the equation for force. So now we can simplify this. Okay, epsilon naught b by d, and here epsilon naught b by d whole square. So one of these will cancel. We'll be left with epsilon naught b by d in the denominator. Okay, so d will go upstairs. Okay, so basically this force comes out to be q square, this d that has gone up, this k minus 1 will remain, k is dielectric constant, and then we'll be left with 2 epsilon naught b here, and this thing will be still squared, so we'll get that L plus k minus 1 into x whole square. So this derivation is as simple as that. Okay, when you look at books, you'll be getting lost in the mass, but here I have tried to make the mass very simple. Okay, the potential energy stored in the capacitor will be q square by 2c. Q is constant, that's why I write the equation as q square by 2c. C is variable. As the dielectric goes in, C will change. We differentiate this equation to get du, and then we find that the potential energy is decreasing. That is being used to do work to move the slab, so that we equate to f dx. Then C and dc we had found out in the previous lesson for a similar situation when the battery was connected, and then we find the equation for force. This force is not constant. This force now depends on x. So here force is not constant. Force is dependent on x. It is a function of x.